What'd we get? Luke? 55 degrees is correct. Now, I do want to talk about how we got 55 because there's several ways you could get 55. Luke, how did you get 55?
I know both ways, but the way I did it was just taking 180 from NL and KL, subtracting 180 from the rest of it, and getting 55 as the last.
Okay, so you looked at it as this being half the circle, and then you added the 65 and the 60 together and took that away from 180. I love it. So you would have done 180 minus, what are those two added together? 125? And that would give you the 55 degrees. Very good. Did anyone do it a different way? Gabby, how'd you do it? You think you know the other way? Okay, go for it. Very good. The entire circle is 360 degrees. You could have added all of them and subtracted that from 360. Tyler, another way? Excellent. This is actually the way that I had never seen before, and someone in my last class got it. Check out this 120, guys. Do you guys agree it's a vertical angle with this angle right here? So you could have just done 120 minus this 65 degrees, and you'll also get 55 degrees, okay? Very cool. You can do this problem a bunch of different ways, but the answer was 55 degrees. Pat on the back if you got it right. Is it a major, minor, or semicircle? Minor. Why? It's less than 180, okay? It's less than half the circle. What about J, L, M? Gabby? 245. I agree with you. How did you get 245?
I added the 120 and the 60 and 65.
Very good. 120, 60, and 65. Or you could have just said JL is 180, right? So then 180 plus 65. Either way, you got the right answer. It is 245. And is that a major, minor, or semicircle, Gabby? It's a major arc. Very good. All right. What about NLK? NLK. Isabella? Very good. And? Excellent. This one's a semicircle. And the one that may have caused us some issues. What about LMN? What about LMN? Bella? 120 degrees is correct. Is it a major, minor, or semicircle? It is a minor, okay? Now I know some of you guys are like, why would they use 3 letters to identify a minor arc? You can use 3 letters for any of these arcs. The only ones where you can only use 2 letters for are which ones? If they use 2 letters to identify an arc, what kind of arc does it have to be? A minor. You cannot use 2 letters and identify a major arc because it needs to tell you which direction to move. We clear on that? But you can use 3 letters for any of these arcs. Understood? Okay. How did we do? Good? Yes, perfect. Okay, what questions do we have from the warm-up? Okay, pull out your homework. Let's go. Created, but the arcs are not the same size. There's a major arc, which is the majority of the circle, and there's a minor arc, which is a smaller one, okay? And that's for any chord that you draw, as long as it's not, what kind of chord? A diameter, okay? Because that will create the 2 semicircles, which are the exact same size, okay? What we're gonna focus on today are these minor arcs, okay? We're gonna focus on these minor arcs in today's lesson that are created by chords. And the first thing we're going to focus on is the congruent corresponding chords theorem. What this theorem says that in the same circle or in congruent circle, so the circles have to be the same size, 2 minor arcs are congruent if and only if their corresponding chords are congruent. So the chords that create those arcs must be congruent in order for the arcs to be the same measure. For example, If these two chords right here, BA and CD, if those are the same lengths, then I know that the measure of the arc AB going along the edge of the circle has to be the same measure as what other arc? CD, okay? As long as those chords are the same size. This theorem also works in reverse. So if you were asked the question, how would you know whether two chords are congruent? How could you answer this question? So if the chords were congruent, we knew that the arcs were congruent. So if we want to know whether the chords are congruent, what do we need to know? The what would need to be congruent? The arcs. The arcs would need to be congruent. Yes. Okay. Second theorem that we're learning is the perpendicular chord bisector theorem. And this theorem says if a diameter, please underline the word diameter, also put or radius, it could be either one. If a diameter or radius of a circle is perpendicular to a chord, that means it forms a 90-degree angle, then the diameter bisects the chord and its arc. This theorem involves a vocabulary word that we've seen before. What does the word bisects mean again? Very good. It cuts it in half. So the radius or the diameter, if it's perpendicular to the chord that we're talking about, so if it forms that 90 degrees, it's going to cut the chord in half, okay? So let's zoom in on this picture. Which of these two is not my diameter, but the chord? FD, who said that? Very good, Camilla, okay? FD is my chord. So if EG is perpendicular, right? And do you guys agree EG is a diameter? If it's perpendicular, it's gonna cut my chord in half. So which two segments in this diagram are congruent to one another? Camilla? Excellent, FH and HD. That's the first part of this theorem. Those two segments of the chords are congruent to one another. But also the two the two arcs that get intersected are also congruent. So what two arcs would be congruent in this case? What two arcs would be the same size? Someone different. Camilla answered my last one. Javonsky? Excellent. DG and GF. Those would also be the same measure as one another, okay? For example, let's just throw one out there. Let's say this one was 35 degrees. Then this one would also have to be 35 degrees. I just made that number up, okay? Now, this theorem also works in reverse. So if you did not know that the segment EG was a diameter, as long as you're given that it's bisecting the chord and it's perpendicular, then now you can assume that it is a diameter and you can put the center of the circle on that line SQ. This is the perpendicular chord bisector converse, okay? So in this case, the big identifier, if you want to make a note of this, in the converse, you do not know that it is a diameter to begin with. You did not see that it was passing through the middle of the circle. Do you guys see that? Your conclusion is, okay, I can add in that it's going through the middle. I know it's a diameter because it's cutting my chord in half and it's perpendicular. Okay? All right. What questions do we have so far? Okay. I know it's very theoretical at this point. It'll make a lot more sense once we start doing the examples, okay? All right, and then our last theorem for today is the equidistant chords theorem, okay? What this theorem says is that if we are in the same circle or in congruent circles, so again, we need those circles to be the same size. The two chords are congruent if and only if they are the same distance from the center, okay? They need to be the same distance from the center. Okay, so for this one, okay, let's talk about it. What are the two chords in this diagram? Gigi? Excellent. A, B, and C, D. Those are my two chords. Now, what this theorem says is that in order for these two chords to be the same length, they have to be the same, like exactly the same distance, okay? They need to be the same distance from the center of the circle. Where's the center of this circle? E. So the distance from E to F, why is EF the distance from this point to AB? What makes it the distance from that point to AB? Why wouldn't this be the distance from that point to AB? Javansky? Why is it the shortest distance? It's perpendicular. Remember, they have to give you this perpendicular symbol so you know that this is the shortest distance. So what this theorem says is that these two chords are only the same length if EF is the same measure as what else? EG. Okay? As long as that distance between that center and each of the chords is the same length, then you know, okay, this chord is the same distance or the same length as this chord. Talk to me. What questions do we have about this theorem? Now, this theorem does not have a converse because it is an if and only if. So it's a biconditional. So remember, in a biconditional, right? Yeah, go ahead. Correct. They have to be perpendicular and the same length, Gabby. Okay? Now, if you knew that the chords were the same length, Gabby, then you already knew, okay, these perpendicular lines from the center to the chord are going to be the same length as well. Okay? So you could be given either one and be asked, okay, can you now conclude? Good question. Any other questions, guys, about this theorem? Okay. So let's go ahead and look at our first example, which is example 1, letter A. We're not only going to we're going to find the value of x and y, and in example B, we're going to find one additional thing, okay? So let's zoom in on example A. And please imagine that like this printed correctly, and this is going through the middle. So this should be a diameter. That red line should be a diameter, okay? All right. What do you see in this picture that could help you solve for x? Bella? 13 and 5 both add up to 18. I agree with that. But why would that help us? You don't know? What is the 13 representing? It's this segment right here, right? From the center down. That's a radius. Do you see another radius on this circle? Where's the other radius? Is that a radius? Why? Does it start in the center and go to the edge of the circle? Yeah. Bingo. So how long is that piece?
13.
Isn't it also going to be 13? Okay. Could we solve for x now?
Yes.
How? The Pythagorean theorem. Very good, Kaden. Can you set it up for me? Excellent. 5 squared plus x squared equals 13 squared. Why was 13 my 13 my C?
Because it's on the opposite side of the hypotenuse.
Excellent. It's across from the hypotenuse. Excellent. It's across from the 90. It is the hypotenuse, okay? All right, let's keep going. This would give me, what's 5 squared? 25 plus x squared equals, I think this is 169.
Yeah.
Then you subtract 25, I believe you get 144. What's the square root of 144? 12, so x equals 12. Simple enough, right? Questions on solving for x? Talk to me. Who thinks they know what y has to be now? If x is 12. Gabby? Y is also going to be 12. Do you know why? Go ahead. Very good. Why is this line down the middle bisecting it? It needs two conditions. It's perpendicular. Very good. That's one of them. And what was the second condition? It's part of the radius or it's the diameter. Very good, Tyler. Okay? So it's perpendicular because we see that 90 and it goes through the middle. It's cutting that chord in half. So I know that these two segments are congruent. So x was equal to 12 and y was equal to 12. Very good. What questions do we have on this one? Okay, let's try the next one. Letter B. Go ahead. All right. We've got an angle of 60 degrees. We've got x down there at the bottom. And we've got y over there on the side. And we've got a radius of 6. What are we thinking? Yep.
Y is 6.
Y is 6. Ooh, y would be 6. I like where your head's at. Y would be 6 if it was saying that y was this whole thing. It's not super clear, but y is actually only this piece right here, okay? But I like what you're thinking, because that would also be a radius, okay? So y should be something less than 6, all right? Do you notice a shape that we're familiar with in this diagram? A right triangle. Let's go ahead and draw that right triangle again, and let's fill in what we know. We know that the angle up here is 60, correct? We know that this angle is 90. This is my y, this is my x, and this is my 6. What else can we fill in this diagram? Tyler? So do you guys agree this is a 30, 60, 90? Okay. What goes across from the 30 degrees? Little a. Very good, Camilla. What goes across from the 60? A times the square root of 3. And across from the 90, the hypotenuse? 2a. Which of these do I set up to solve? Which one isn't a variable? The 6. How could I solve 6 equals 2a? How could I solve that for a? Divide by 2. So you would get 3 equals a. Do you guys agree? Use that a value in the other two. What's the value of y? 3. Excellent. And what is the value of x? 3 times the square root of 3. Excellent. Okay? Now, this problem also gave you a second part. Okay? It also wants to know the measure of the arc AB. So the measure of this arc starting at A and going around to B. Let's think about it. Camilla? What's that? 6? Well, remember, it's going to be in terms of degrees, okay? It's going to be in terms of degrees. Any ideas? Javansky? 720? How many degrees are in a circle? 360. Is this more than a full circle? No.
I was thinking, I didn't read the entire question.
Okay.
See, if it
Yes, it could have been 180 if it was in the middle, right? But this is actually a chord, not a diameter, so it's not going to be 180. I have a question for you guys. Is this a central angle? Is its vertex in the middle?
Oh.
What is the measure of this arc right here? How many degrees? It's 60 degrees. Because it stems from a central angle. Do you guys agree? What would the measure of this angle have to be and why? Tyler? It's also 60 degrees. Now, the why is very important, okay? Tyler admitted he did not know why. The reason is this line down the middle, is that a radius? Is it a radius? Yes. Is it perpendicular to the chord? So do you guys agree it's cutting this guy in half and the two arcs in half? So therefore there must be symmetry there, okay? So if one half is 60, the other arc needs to be 60, and together what do they make? 120 degrees. Talk to me. I can see we have some questions. What questions do we have? Go ahead, Gigi. The lines that are confusing? What if we erased everything and started from scratch again? So Gigi, I want to point something out to you, right? I'm glad that you spoke up, okay? If you ever have this case where you have a radius or a diameter that is perpendicular to a chord, correct? It cuts this chord into two equal pieces. It bisects the chord and it bisects the arc AB. So now this piece of the arc is also congruent to that piece of the arc. Cool? Why is actually, it's asking for this side right here, where it stops, where the chord meets the radius. Okay? And we found why when we set up that triangle. Okay? What we're trying to find is the measure of AB, the arc. Okay? What other questions? Yeah, Veronica. Could I have used sine? Yes, you could have used sine. You're talking about for the inside of the triangle, correct? Yes, you could have used sine as well. You would have done sine of 60 equals x over 6? Yes. What else? Okay. Moving on to C. Yep, I know. Thank you. All right. What are we thinking for C? Gigi? We're going to solve for x and y, okay? But I like how you pointed out that these two are perpendicular, okay?
Which means that those chords are the same length. So if 8 is that half of the chord, so 8 plus x is also
Correct. 8 plus x, we know that these two chords, right, must be the same length as y, right? Because what Gigi pointed out was that these chords are the same distance from the circle. Because here's the center, right, from the center of the circle. This distance is the same as this distance because of those congruence marks. Excellent. So now we know that 8 plus x is equal to y. Guys, if I extended this line and made it a radius, do you guys agree that this is now a radius that's perpendicular to a chord? So now it's cutting it in half as well. So we know that x is the same length as 8. So x equals 8. And if you plug that 8 into here, what is y equal to? Y is equal to 16. This is where we're going to stop, guys. So after this one, go ahead and turn in your notes. The homework for 10.3 is due on Friday. I recommend you get a decent chunk of it done today. We have 2 more examples in the notes, and then we're done.
Okay, in example 2, we have to find the measure of the arc CD. CD is this arc right here, going from C along the edge of the circle to D. Now, remember, we do know that as long as BD goes through the middle, right, as long as it's a diameter, and it forms a 90-degree angle with the chord, it is bisecting the chord and the arc that's created from that chord. So we know that we can set 9x equal to 80 minus x because those 2 arcs should be the same measure. So now all we're going to do is add x to both sides. We're going to get 10x equals 80. Divide by 10, divide by 10. You're going to get x equals 8. Once we get the value of 8, we're going to plug it in to find the measure of our arc for CD. We're going to get that CD is going to be the measure of the arc CD is going to be 9 times 8 degrees, and that's going to be 72 degrees. So that's the measure of the arc CD. All right, moving on. So then this one, example 3, is an example where we have 2 chords that are the same length in the same circle. So I know that QR, this red chord, and this red chord, ST, are the same length. And remember, for chords that are the same length, then I know that the distance they are from the center, C, so this is the distance from the center, this is the distance from the center, that those 2 lengths are the same. So I can also go ahead and set 2x equal to 5x minus 9. And then we're going to go ahead and solve for x. We would subtract 5x from both sides. We would get negative 3x equals negative 9. Divide by negative 3. Divide by negative 3. You're going to get x equals a positive 3. So we have x equals 3. And it wants us to find CU. Again, we're going to have to take that 3, plug it in for whatever was representing CU. In this case, it's 2x. So we're going to say CU equals 2 times that 3. And we're going to say CU equals 6. So we know CU is 6 units. Now, I want to take this problem a step further. Let's say this problem asks you to find the radius. Okay? So the radius, none of these lines that are given represent the radius, okay? But let's draw our own radius, and I'm going to draw the radius from Q, which is on the edge of the circle, to the center. That is the definition of a radius, okay? Now, once I draw that radius, I'm going to notice that there's a familiar shape for me. There is a right triangle between C, U, and Q. I know it's a right triangle because the angle on the other side was 90. Therefore, this side also needs to be 90. Remember, we just found CU, so it's not 2x anymore. It's 6. We just found it. And this length is, and this entire length is 16. But remember, this could also be a radius if we extended it. And then that radius is perpendicular to this chord. Therefore, it's bisecting it as well. So I know that this 16 is going to be divided in half, and it's going to be 8 on this side. So I have a regular right triangle where I know 2 of the lengths. I'm missing the hypotenuse, which will eventually be my radius, okay? So I can set up the Pythagorean theorem. I'm going to say a squared, which I'll make 6 squared, plus my b squared, which will be 8 squared, is equal to my radius, which I'll represent by r. That's this side, QC. And then I'll be squaring it as well. All right, so then I go ahead and solve. I'm going to get 36, 6 squared is 36, plus 64 equals r squared. We're going to go ahead and add 36 and 64. We get 100 equals r squared. And then we take the square root of both sides, so that way the square will cancel. And we'll get r equals, the square root of 100 is just 10. So my radius is 10. All right, guys? So on these types of problems, you may have to draw your own radius if it's asking you for the radius. It just needs to go from the center of the circle to the edge and connect at a point so that it forms a right triangle.